Hello, everyone. So last time we looked at the topic of implicit differentiation. And we saw how if we have an implicit equation, let's say if we have an equation of the form, let's say f of x and y equals 0, then we saw how to compute y prime or dy to dx. So basically we said that we have to differentiate both sides of our equation. And the only thing that we have using derivative rules, and the only thing that we have to remember is that derivative of the terms containing y must be computed using the chain rule, meaning that they have to be multiplied with y prime. So derivative of x squared is 2x, for example. Derivative of y squared, however, will be 2y times y prime. Okay, so let's look at an example of this implicit differentiation, an application basically. So let's say logarithmic differentiation. So let's use the formula for the derivative of exponential functions So we already know that d to dx of e to power x is e to power x, right? So let's use this formula to find d to dx of ln x. We already provided a formula for d to dx of ln x. We mentioned that it has to be 1 over x, and we proved it using the definition of E, one of the definitions of E. But this time we want to derive the formula for d to dx of ln x using the formula for d to dx of e to the x. So we assume that we already know the formula for d to dx of e to the x, which is e to the x itself. And we want to use it to find d to dx of ln x. So let me put or set, let's say y equals ln x, right? Then if I want to translate this into exponentials, how can I rewrite this equation? Because we already know that, if let's say log a in base b equals c, this is same as saying that a is equal to b to power c, right? And ln means logarithm in base e. So logarithm x in base e is y, so that means e to power y is equal to x, right? So this can be rewritten in the form e to power y equals x. Now, I have an implicit equation. This is an implicit equation for y. This one is explicit equation for y. What was the difference between explicit equation and implicit equation? Well, it was simple. If you have some equation of the form y equals some function of x, then it's explicit. Anything other than that would be considered implicit. So first equation is y equals a function of x, so it's explicit. But the second equation is it's not of that form. It's like e to power y equals x. So this is considered implicit. So how can we use this implicit equation to find y prime or dy to dx? Now to find y prime equals dy to dx, differentiate both sides of equation above, right? So this is the recipe that we provided earlier, that, you know, to find y prime with dy to dx, just differentiate both sides. Then what do we get? E to power y derivative equals x derivative. Now e to power y derivative, what is it? So we just said in the beginning that derivative of terms containing y is the usual derivative according to a chain rule. The derivative will be the usual derivative times y prime. So the usual derivative for e to the x is e to the x. So derivative of e to the y will be e to the y. So by implicit differentiation, or I can say by chain rule, e to the y times y prime. The usual derivative is e to the y, then multiplied with y prime. And what is derivative of x? Derivative of x is 1. So that gives y prime equals 1 over e to power y. Right? So after you differentiate both sides, then you need to isolate for y prime and solve for y prime. I don't need to isolate because it's just one term containing y prime. It's already in one side and the other term in the other side. So once I solve for y prime, I get y prime equals 1 over e to the y. And what was e to the y? E to the y was x, right? Yeah, e to the y equals x. So e to the y, because it's x, so then we can say that y prime equals dy to dx equals 1 over x. So this is derivative of ln x that we showed using this method. We showed that it's 1 over x. So we already saw that the conclusion of this formula before, but because it's very important, let me repeat that conclusion, that, or corollary. Usually in mathematics, instead of conclusion, we say corollary. Let y equals ln u, then y prime equals dy to dx is equal to u prime over u, where u equals g of x is a function of x. Why is this true? This is again because of chain rule. Dy to dx is same as dy to du, which is 1 over u by this formula here, times du to dx. Du to dx means u prime. So 1 over u times u prime, or u prime over u. This is a formula we have seen before as well, but I want to repeat this. So for example, y equals, let's say, ln x squared plus 1. Then dy to dx will be equal to derivative of x squared plus 1 divided by x squared plus 1. And that's 2x over x squared plus 1. Okay. Now, we want to talk about logarithmic differentiation. So logarithmic differentiation is a method to find derivatives. And what is the advantage of this method? And simplifies, and this method simplifies expressions using properties of logarithm. For example, we know that log AB is equal to log A plus log B, or log A over B equals log A minus log B. And we also know that log A to power M is equal to M times log A. So we can use these properties of log to simplify some normally long expressions and use them to find derivative of a given function. So let's look at an example. Let's say y equals root x times x squared plus 1 to power 5 divided by 3x minus 1 to power 6 times 7x plus 1, 7x squared plus 1 to power 8. Find y prime equals dy to dx. So this is a expression, is a fraction. You want to find a derivative of a fraction or a quotient. Of course, you can use quotient rule, right? So this question can be solved without taking logarithm or without a logarithmic differentiation. So it still can be done, but it's going to be long because you have to use quotient rule, and for quotient rule you need derivative of top and derivative of bottom, but each of top and bottom is product of two functions. So again, for them you need the product rule. And even after you want to use product rule, you need to, for example, find derivative of this guy here. And because there is a power here, you have to use the power rule and the chain rule as well, because it's not x to power 5, it's like u to power 5. So you can find y prime without logarithmic differentiation, without taking logarithm, but it's going to be long. But if we apply logarithmic differentiation, if we take log from both sides of our equation, then we can find y prime much faster, because then we can apply, take advantage of, properties of logarithm to simplify our expression first, and then we can easily find y prime. So let's say solution 1, use quotient rule, quotient, product, and power rules combined with chain rule. Chain rule to find y prime equals dy to dx. So this one that we leave as exercise. Solution 2. First, take ln from both sides to simplify the expression. Then differentiate both sides. Both sides to find y prime equals dy to dx. So this one is called, this method basically is called logarithmic differentiation. Okay, so what is our function? Y equals root x. Okay, we have y here. Let me not repeat it. Now we are saying that in logarithmic differentiation, first take ln from both sides and simplify it using logarithm properties. Then differentiate both sides. So if I take ln from both sides, left-hand side becomes ln y. So ln y equals what about right-hand side? Right-hand side, I will have ln of this fraction. Ln of this fraction means ln of top minus ln of bottom, according to the logarithm properties, right? Ln of a fraction is ln of top minus ln of bottom. So I can write this one as ln of root x times x squared plus 1 to power 5 minus ln of bottom. So bottom is 3x minus 1 to power 6. Three x minus 1 to power 6 times 7x squared plus 1 to power 8. Now I have ln of product of two functions. I can write them as ln of the first plus ln of the second, right? So ln of root x means x to power 1/2. Power can be also taken out, right? So I'm using, see, I wrote 3 important properties of logarithm here for you. Logarithm of, first we wrote logarithm of quotient as logarithm of top minus logarithm bottom. Then logarithm product is logarithm first plus logarithm second. But for each term, if we have a power, we can take the power out. So logarithm root x is our first term, and root x means x to power 1/2. So power 1/2 can be taken out. So 1/2 ln x plus, right? So ln of product of these two means ln of first plus ln of second. Now for ln of second, again, second term here has a power. The power is 5. So I can take the power 5 out. So plus 5 times ln of x squared plus 1, right? So I took the power 5 out. And then again, this one, ln of first plus ln of second, each one has a power. Power can be taken out. So minus 6 times ln 3x minus 1 minus 8 times ln 7x squared plus 1. So ln y equals this expression here. Now we have to differentiate both sides, differentiate both sides. So ln y derivative, what is it? It's ln of a term. We said that the derivative of terms containing y is the usual derivative times y prime. So ln x derivative is 1 over x. So ln y derivative is 1 over y times y prime. So ln, so it's going to be y prime over y. Okay, so ln y derivative is the usual derivative 1 over y times y prime, according to the chain rule, according to what the recipe provided for implicit differentiation. So basically, this is an implicit equation because it's ln y equals some expression. So we said that if it's y equals some function of x, then it's explicit. Anything other than that is implicit. So ln y equals a function of x is still considered implicit. So to differentiate, we have to use implicit differentiation, the recipe that we gave last time. The derivative of terms containing y is the usual derivative times y prime. I also wrote just a few minutes ago the same rule about u. And u is u prime over u. But here instead of u, we have y, but still the same concept because, well, u is a function of x here, and here also y is a function of x. So still same concept as the formula that I wrote a few minutes ago. So y prime over y equals, now for the right-hand side, 1/2 ln x. We just said ln x derivative is 1 over x. So 1 over 2 times 1 over x plus, now this one is ln u. Ln u, we said what? U prime over u. So 5 times x squared plus 1 derivative divided by x squared plus 1 minus 6 times, similarly this one, ln u, derivative is u prime over u. Minus 8 times 7x squared plus 1 derivative divided by 7x squared plus 1. And then this is 1 over 2x plus, so this one derivative is 2x. So basically here we use two facts, ln u. Derivative is u prime over u, and ln y derivative is y prime over y. Okay, so these are the formulas we have used here. So 1 over 2x, so y prime over y equals 1 over 2x, and x squared plus 1 derivative is 2x, so times 5 is 10x, so plus 10x over x squared plus 1 minus, so 3x minus 1 derivative is 3, so times 6 is 18, so minus 18 over 3x minus 1. And 7x squared plus 1 derivative is 14x times 8 is 112 x divided by 7x squared plus 1. Okay. And then, so this is y prime over y, right? And you want to find y prime. So we're almost done. We just need to multiply both sides by y. And we will find y prime. So y prime will be equal to dy to dx equals y times this expression, 1 over 2x plus 10x over x squared plus 1 minus 18 over 3x minus 1 minus 112x over 7x squared plus 1. And we also know what y is, right? So then that means y prime equals dy to dx equals, what was y? It was that long expression, root x times x squared plus 1 to power 5 divided by 3x minus 1 to power 6, 7x squared plus 1 to power 8, and then times this expression times 1 over 2x plus 10x over x squared plus 1 minus 18 over 3x minus 1 minus 112x over 7x squared plus 1. Okay, so we found y prime or dy to dx using logarithmic differentiation. Let's look at another formula. Let y equals x to power x. Find y prime equals dy to dx. Okay, so normally the functions that we saw before, so the variable x either appeared in base or in the power. So it's very important. It's a little bit tricky. If the variable x appears in the base, so let me write here. So far, note. So far we saw that if you have, if x appears in the base, for example, let's say x to power 10, then use a power rule to differentiate. So x to power 10 derivative is 10x to power 9. So this is one case. Another case, if x appears in the power, for example, 10 to power x, then we have to use exponential differentiation, use exponential differentiation to find the derivative. So 10 to power x derivative will be 10 to power x itself times ln 10. Right? E to power x derivative besides e to power x itself, but a to power x derivative is a to power x itself times ln a. Okay, so this is very tricky situation. If x appears in the base, use this formula. If x appears in the power, use this formula. What about this example? This example, x appears both in base and power. So the third case, if x appears both in base and the power, see this example, x to power x, then we can we cannot use power rule or exponential differentiation to find the derivative. For power rule, the power must be constant. For exponential rule or exponential differentiation, the base must be constant. So if x appears both in base and the power, then we can use neither power rule nor exponential differentiation. What should we do instead? If we cannot use any of these two rules, what should we do? Well, we have to use logarithmic differentiation. So in such a case, use the logarithmic differentiation to find y prime equals dy to dx. So y is equal to, again, let me say x to power x, then ln y is equal to ln x to power x. Right, so logarithmic differentiation means take ln from both sides first, then use logarithmic properties to simplify, and then differentiate both sides. So I took ln from both sides. Now right hand side is ln x to power x. If I use logarithmic properties, I can simplify it as x times ln x, right? Because the power can be taken out. So I can write it as x times ln x. Now I can differentiate both sides. And what will I get? I'll get ln y derivative is equal to x times ln x derivative. X times ln x derivative, I have to use the product rule. And ln y derivative, I can write it as y prime over y. We just saw in the previous example. And x times ln x, use product rule. So derivative of the first function, which is x. So x derivative times ln x plus x times ln x derivative. Derivative of x is 1, so ln x plus x times derivative of ln x is 1 over x. So that's going to be 1 plus ln x. So y prime over y is 1 plus ln x. So what will be y prime? Therefore, y prime will be equal to y times 1 plus ln x. And we know y is x to power x, so x to power x times 1 plus ln x. So we showed that y prime equals dy to dx equals x to power x times 1 plus ln x. All right, let's look at the next example. Let y equals, let's say, x squared plus 1 to power sine x. Find dy to dx. So again, see, but first, the very first thing you have to see, like I said, is that the variable x, does it appear in the base or power or both? If it's just in the base, then you can use power rule. If it's just in the power, exponential rule. And then if it's both, then you have to use logarithmic differentiation. So let's take ln from both sides. So again, since the variable x appears both in the base and the power, we will use logarithmic differentiation. So then we get ln y equals ln. So logarithmic differentiation means we have to take ln from both sides and then use logarithm properties. So ln y equals ln x squared plus 1 to power sine x, and then power sine x can be taken out. Sine x times ln x squared plus 1. Now we can differentiate both sides. The red tractor drives up next to the forager. Differentiate both sides, then we get ln y derivative. We saw in the previous examples that it was y prime over y. And for derivative of right hand side, again, we have to use the product rule. So for product rule, so derivative of a first function, sine x derivative times ln x squared plus 1 plus sine x times derivative of the second function, ln x squared plus 1 derivative. So then this is cos x times ln x squared plus 1 plus sine x times now derivative of ln x squared plus 1. Ln u derivative, we know it's u prime over u, so it's going to be 2x over x squared plus 1. And that's it. So then y prime is equal to y, and y, we know that, what was y? Y was x squared plus 1 to power sine x. So y prime is equal to this y, which is x squared plus 1 to power sine x, times cos x times ln x squared plus 1 plus sine x times this guy. So it's going to be plus 2x sine x divided by x squared plus 1. Okay, so this is the derivative of y, which we calculated using logarithmic differentiation. Okay, now let's look at how we can calculate derivative of inverse trig functions. Derivative of inverse trig functions. So let's start with sine inverse x. So first of all, let's remind ourselves about the definition of sine inverse. So we said that, sine inverse, if we say, let's say theta equals sine inverse A, so this means that sine theta is equal to A. And also it means theta is between minus pi half to pi half. So the output of sine inverse is always between minus pi half to pi half. And the input here, A, is of course always between -1 to 1, because remember, inverse function changes input with output. So for sine x, the input is chosen from minus pi half to pi half, the output between -1 to 1. So for sine inverse, the input becomes between -1 to 1, output becomes between minus pi half to pi half. So now let's say, let y equal sine inverse x. And we want to find a dy to dx. Okay, we want to use a similar method that we previously used. For example, for logarithm, we changed it to exponential, right? So we translated logarithm to exponential, and then we used the formula for exponential differentiation to find the derivative of logarithm. So we can use a similar method here. So y is equal to sine inverse x. So we can translate to original trigonometric function. So how can we do that? So we have y equals sine inverse x. So this means that sine y is equal to x. Sine y is equal to x, right? Now we can differentiate both sides. So again, see, we basically transform the explicit equation to an implicit equation. This is explicit equation because it's an equation of the form y equals some function of x, but this is an implicit equation because it's not of the form y equals a function of x, with sine y equals x. Now we can use implicit differentiation to find y prime. So now use implicit differentiation. And what do we get? We get d to dx of, or let me write it this way, that sine y derivative is equal to x derivative. So sine y derivative, so the derivative of a term containing y, what is it? It's the usual derivative times y prime. So see, we are just repeating, I'm just repeating this sentence over and over since last lecture. That derivative of a term containing y is the usual derivative times y prime. The usual derivative of sine y is cos y. So cos y times y prime, or in other words, y prime times cos y equals derivative of x, which is 1. And then that gives y prime equals 1 over cos y. 1 over cos y is a formula for y prime, but our preference is to, so this formula is correct, but our preference is to write a formula in terms of x for y prime, because see, originally y was given as a function of x, sine inverse x. So our preference is to have a formula again only in terms of x for y prime. So y prime right now is 1 over cos y. How can I write it in terms of x if I want to write the answer in terms of x? See, I know that sine y is x. Sine y, we know it's x. So if sine y is x, what will be cos y? So now, to write the answer in terms of x, to write the answer in terms of x, in terms of x, and note that sine y is equal to x, right? So sine y equals x, we had it here. So what will be cos y? So thus, we can say that cos y is equal to square root of 1 minus sine squared y. So why is that true? Cos y is root 1 minus sine squared y, because cos y is positive actually. Why is it positive? See, y is sine inverse x. So it's an output for sine inverse. We just said that the output for sine inverse, look at here, Here I denoted with theta. We said that the output for sine inverse is between minus pi half to pi half. So quadrant 1 or 4. And quadrant 1 and 4, y is cos of the angle in quadrant 1 and 4 is positive. So if y is equal to sine inverse x, it will be in the quadrant 1 or 4. Therefore, cos y will be positive. So see here, I can explain that. We chose root 1 minus sine squared y. And not minus root 1 minus sine squared y, since y equals sine inverse x is in quadrant 1 or quadrant 4, hence cos y will be positive. And if cos y is positive, then we won't choose minus root 1 minus sine squared. We'll just simply choose positive root 1 minus sine squared. So cos y that we had here is root 1 minus sine squared y. But what is sine y? Sine y is x. I just wrote here, sine y is x. So this is root 1 minus x squared. Here, see, we just said sine y is x. So root 1 minus sine squared y will be root 1 minus x squared. So that means y prime will be equal to 1 over root 1 minus x squared. So we showed that if y is equal to sine inverse x, then we can say y prime equals dy to dx equals 1 over root 1 minus x squared. So this is the way that we could find the derivative of sine inverse function.